Okay. So today we'll be looking at systems of linear equations. So of course the institute is Vispa Institute of Technology. Introduction to Machine Learning, specifically linear algebra. Then today, which is lab 6, we'll be looking at systems of linear equations. Then these are the learning outcomes. By the end of this session, um, okay, by the end of this session, students should be able to understand and work with linear systems in machine learning. Last week, you remember we did Gaussian elimination, so we may not really talk much about it. The matrix inversion, sorry, the matrix inverse or inversion, yeah. Then solving AX equal to B using the inverse, numerical stability, and other alternatives. Okay, so we'll just start right away. So this very first cell is just important libraries, and over here, this is just by the way. It's not really important, but this is just by the way to let you know what exactly these codes are trying to do. So the NP, so the NP dot set underscore print options, all those things. So precision equal to 4 says that show only 4 decimal places throughout your codes. And suppress equal to true, which means do not use scientific notations. Okay, you see sometimes we have an expression when you do your computation, you get an expression like 1.3 e and then minus what 0.5. Okay, so instead of this scientific notation, just show 0.0001. Okay, so this is just by the way, it's not really important. So this was just like an example, just something, just a simple example to print numpy.array, and you realize we got 0 and we got so you realize we got your answers to 4 decimal places. Okay, 0 is obviously 0. We could have been 0.000. Okay, the 4 zeros, but yeah, so just that's it, just by the way. So our very first concept will be the very first concept to be talking about will be linear systems, that is AX equal to B, and how it is the core of machine learning. Okay, so these over the past 2 to 3 weeks, we've been talking about linear systems, linear systems, linear systems. Okay, so great. So over here, with as usual, AX equal to B. A is a coefficient matrix. It represents that a linear transformation. X is some unknown vector or the solution we are looking for, okay, the unknown. And B is our target vector, okay, where AX must land, if you remember during last week's lectures. Okay, so this is some simple quotes, okay. A is that matrix, okay, so meaning if we want to write A as 1, it becomes -5 to -4 1, okay. And remember, all this I've been saying, a matrix is a pattern list of lists. We've been saying that by a matrix we are looking from things from in terms of the row, okay, one row getting stacked upon the other, where position really matters, okay. And B is your vector, okay. In this case, it's just -2 and -4, right? So these are some print function: print A, print B, print the word system, print what -5x plus 2y equal to -2. So these, right, that is just by the way. We've already defined A here, and we are just telling it to print it out. Okay, great. So obviously, A creates a 2 by 2 matrix, obviously, which is -5 to -4 1. Okay. Then Usually we use the d type equal to float. Okay, we use the d type equal to float because it forces all the numbers to be floating point values. Okay, so that is just by the way. Okay, so you realize that we printed results negative 5x plus 2y equal to negative 2. Okay, this is the same as what we've represented here. So a equal to x equal to ax equal to b. Okay, don't be confused. What does it mean? It means if you take your matrix A, it is what? It is negative 5 to negative 4 1, right? And x over here is xy. Okay, don't be confused. Or we can just use a different variable instead of x. So maybe let's say ac equal to b, right? A capital letter small c equal to b. Okay, where c is your x and y. Okay, and if you remember, equal to b, right? Where b is that vector what? Negative 2, negative 4. Okay, so if you solve this, if you solve the matrix multiplication for a times c, which is your xy, you should be getting this equation down here. Okay, that is negative 5x plus 2y equal to negative 2 and negative 4x plus y equal to negative 4, right? I hope you understand up to this point. As easy as this. Great. Now we move on to the next concept. We move on to the next concept. So over here, you realize we were just making use of NumPy. Initially, we'll try to understand how things works with Python. Then we'll make use of NumPy to see if you're going to get the same thing. But over here, we just went straight ahead. So this lab, we'll just use NumPy. I mean, we've gotten used to Python programming, right? So this lab, from this lab onwards, we just make use of NumPy libraries, NumPy, instead of trying to understand raw Python codes and getting to understand how it's implemented in NumPy. Okay, great. So we are getting to the second concept, okay, that is determinants. That's existence and geometric meaning. Okay, so we'll get to understand this in a bit. So a unique solution, of course, exists if the determinant of your matrix A is not equal to 0. You agree, right? And we say the determinant of A or the determinant of some matrix is the signed area scaling factor of the transformation. We'll be seeing some visualizations later so you will understand what I'm saying. But when we say determinant, okay, determinant of A, remember we said um, the determinant is some scaling factor. But this lab, we are trying to understand what specifically is that scaling factor. And we said the determinant of A or the determinant of some matrix A is the signed area scaling factor of the transformation. Okay, so for example, say we have a 2 by 2 matrix. Okay, in this example, we just I mean, we are just trying to make should I say life easier for ourselves a bit, just to understand what is happening. So we just made use of a 2 by 2 matrix. Okay, we just made use of a 2 by 2 matrix. um and we are saying that for a 2 by 2 matrix, to find the determinant, okay, so we are saying that we are assuming that some matrix A or some matrix Y or some matrix, okay, say it has elements A, B, and C, D, okay. If we want to get the determinant of that particular matrix, what do? We multiply elements A by D and minus B times C, okay. As easy as that. You remember what we did last week, okay. Great. Then this is just some simple things you should know. So absolute value is equal to what? The area scaling factor of the linear transformation. Right? And depending on the sign helps you know the orientation. Positive, preserved, negative, reversed. Okay. We'll understand that during the visualization. Okay. Okay. We'll be going there in a bit. Great. So this code, okay, this simple codes we have over here. Very simple. If we were using normal raw Python programming, we'll have a lot to type. But as usual, we have NumPy, which is a Python library. Okay, we make it this helps us make life easier. No need to type plenty codes when you just want to achieve the same goal, right? So to find the determinant of A, we use this notation that is np dot linalg dot DETA. All this expression to find the determinant. So it's very easy to remember, right? So to find the determinant of the matrix that you defined here earlier, remember A was this, right? A was -5 to a -4, 1. Remember, right? Great. So A A is what? NP. To find the determinant of A is this whole expression into brackets A. We want to find determinant of A. Okay, great. And the second line over here is trying to do something, right? It's so first of all, it's trying to print the determinant of A in 4 decimal places. Okay, so that is what they did here initially. So DET underscore A, then the colon dot 4F. Okay, it printed the determinant of A in 4 decimal places. Then it also decided to check if a unique solution exists. We said a unique solution exists if the determinant is not equal to 0, right? So that is what they try to check with this NumPy expression here. Easy to grasp and understand, right? Great. So it checks if the determinant is not equal to 0. Okay. So first of all, let me break things down. So this expression, I hope you can all see what I've highlighted. This expression over here, okay? It's checking if the determinant is approximately 0. Okay, so if we bring the not, if we put not in front of it, what does it mean? It's trying to check for the opposite way. It's returning
Oh, you are not audible again.
hello.
Hello?
Yeah.
Your voice is going up and down. Like, I couldn't hear what you were saying.
Oh, sorry. Please, up to is it what I'm just explaining or so far?
This particular
Okay,
one.
okay, okay. Then let me explain it again. So I was saying that this particular lines of codes, okay, this very first one is the expression NumPy uses to calculate for the determinant of your matrix. And you remember we defined the matrix A over here in this cell as -5 to a -4, 1. You remember, right? So since we've already defined it here, we don't need to write it again, right? So if you just want to find the determinant of A, is D E T underscore A, all this expression then into bracket A, okay? Just to find the determinant using NumPy. Then we have this second line of code. Okay, and I was saying that so over here print DET underscore A, then what colon dot 4F. And I said that dot 4F means your answer, it should give you your answer in 4 decimal places. So we've already calculated the we've already calculated the determinants initially, but now we want it to print in 4 decimal places, okay? And that is the very first thing it did. Then the second one is to check if the unique solution exists. And we said that if the unique solution truly exists, what does it mean? It means the determinant is not equal to 0. And that is what this particular line of code is trying to do. And I was trying to say that the NP dot is close DET underscore A0. That expression alone is checking if the determinant is approximately 0. But because we've placed not over here, okay, it tries to do the opposite. So what I was trying to say was we got true because the determinant was not 0, right? And truly is a unique solution. If it was false, it would have been that the determinant would have meant that the determinant was 0 and hence no unique solution. Okay, that is it for this part. And of course, if we say the determinant is not equal to 0, the matrix is invertible or the system has exactly one solution. You remember from last week's lectures. And if it's 0, it means the matrix is singular and the system is either inconsistent, no solution, or it has infinitely many solutions. Sorry. So this one is just some visualization. No need to really understand the codes that is happening here. But this is just some unit area or some array of some matrix we defined, okay, to just get some square area, okay. This is what we defined to get a unit square, a sum matrix or some Python list of lists. Transformed over here is what? This times what? A. You remember? So you remember that it was this initially that we transformed it by multiplying it or doing a matrix multiplication by A, okay, which is already defined at the very top, -5, 2 and -4, 1, okay. So then we have this visualization. Let me try reducing it. Okay, so we have this visualization over here, okay. You see that you realize that before transformation, okay, this was a unit square area. Then after linear transformation, we got what? The area to be 3.0. Remember, the area over here is the determinant. Okay, so the area over here is a determinant. That's the 3.0 we got initially. Okay, so over here we can see that we realize that this figure shows that the linear transformation changes the shapes. You agree, right? Specifically how the matrix A transforms the unit square and how the determinant we've gotten, okay, relates to area scaling, right? I hope this is clear to you. Okay, that we multiply some matrix A by the unit square matrix and it transformed to give you this, should I call it, is it pink, orange? Yeah, that's parallelogram, transform parallelogram. Okay, so in all, this is just to basically understand what we mean by transformation, why the determinant is important on the first place, and all that. So again, the determinant is the sign area scaling factor. Okay, the sign area scaling factor or the area scale. Okay, so before transformation, we had a unit square. Then after we multiplied it by some matrix A, which we already defined earlier, we got this transform parallelogram. Okay, great. Now we are moving on to another concept called the Cramer's rule. Okay, so in the next concepts, we'll try to understand how um, the systems of linear equations are done. Okay, so you remember last week the Gaussian elimination. We tried to do some Gaussian elimination to find the unknown solutions. Okay, so if you have ax equal to b, okay, if you have matrix A, you try to and so if you have matrix A, some vector, let me say some vector C which has elements x and y equal to b. Okay, if you try to we are trying to find the unknowns, and over here our unknowns will be x and y. Okay, so remember last week the Gaussian elimination we did, it was, of course, it was too long. It was too long because first of all it was a 3 by 3 matrix. Okay, but what I'm trying to say is there are so many ways to solve for your unknowns. Okay, there are so many ways to solve for your unknowns, and you understand how different machine learning models make use of these concepts. Okay, you understand how they make use of these concepts. So meaning a third concept is the Kramer's rule. Okay, so it says replace column I, replace column I of A with B. Okay, giving you a ratio of determinants which gives the ith coordinate. So for now, this might look a bit abstract to you. Um, I'm hoping maybe if I explain, you'll be able to understand or be able to picture it if I'm mentioning the numbers. Okay, great. So okay, then next we have method one, which is matrix inverse. Okay, of course you remember to find for your unknown, we make use of s equal to negative 1b. Okay, this is also another way to find your unknown. So to find your unknown, we can use Cramer's rule, we can use matrix inverse. Okay, so let's try to understand both concepts in quotes. Okay, great. So we have this very cell of quotes. Okay, now let me break things down for you to understand what it's trying to do. So you remember, if we have you remember the value of matrix A we've been using all this while. Please grab a pen and a paper, just in case you're not able to understand the abstract things I'm saying. If I'm just speaking, you may not understand me. Okay. So remember the system of equations that was defined way earlier, because we had our matrix to be negative 5, 2, negative 4, and 1. Okay. So to transform all those expressions into a system of linear equations, remember we have negative 5x plus 2y and negative 4x plus y. Sorry, negative 5x plus 2y equal to negative 2. Okay, let me not confuse you. And negative 4x plus y equal to negative 4, right? This is the same as ax equal to b. Okay, right? You get me, right? Okay, great. Kramer's rule is saying that x, okay, x is equal to dt a superscript x det a. Then you ask yourself, what do you mean by a small x? Okay, what do we mean by that expression? What do we mean by this expression over here? What do we mean? Okay, so it's saying that your a, so we have x for the Kramer's rule. Okay, this is for the Kramer's rule. This x is equal to what? The matrix A superscript x is the matrix A with its first column replaced by the vector B. Let me take it again. So we have x is equal to det into brackets A superscript x all over det A. Okay, determinant. So finding determinant of some A superscript x, small x beneath there, if you don't understand superscript, all over det what age, determinant of a. Remember, I've already calculated that and it was 3. Okay, and y. So over here, we are trying to find the unknowns. Okay, if you have a system of linear equation with some matrix A, and instead of x, I'm placing c there equal to b. We are trying to find the element of the unknown, sorry, that is x and y. Okay, and that is what Kramer's rule is trying to achieve over here. Okay, so to find x alone, we said x is equal to dt bracket a superscript x over dt a. Okay, and ax is the matrix A with its first column replaced by the vector B. Okay, so first of all, what is our matrix A? Our matrix A was what? Our matrix A was negative 5 to negative 4 and 1. And we are saying that if this is A, then AX is what? Matrix A with its first column. You remember the difference between row and column. With this first column replaced by the vector b, so what? Um instead of -5, -4, okay, instead of column -5, -4, remember the matrix A is -5 to -4 and 1. So instead of -5 for being the first column of A, we replace that with the vector B, which is what? -2 and -4. So now your new matrix, or your subscript X, becomes what? -2 to -4, 1. Okay, that is the same. So once we have this matrix, once we have A small x, or subscript X, okay, all over. So this new matrix we've gotten, okay, we are trying to find the determinant of it. All over the determinant of your A, which was -5, 2, and -4, 1. Okay, you realize how easy it is. Okay, great. Then y, same as y. Okay, ay is the matrix A with its second column replaced by the vector B. So again, you have your matrix A, which is -5 to -4 and 1. We look at the second column, which is 2 and 1, and try to replace it with your vector B. So now it becomes what? -5, -2, and -4, -4. Okay, you agree with me? So again, you pick the same formula. Your y is equal to determinant of your new matrix, okay? Your new matrix where you replace with a vector b all over the determinant of A that was already calculated. Okay, so that was it, by the way. So that is what this code was trying to achieve. That is what this lines of code was trying to achieve. Okay. So if we take this example like this, if we take this like this, what that code is trying to do is it tries to make a copy of A, that is A dot copy, first of all. Then it replaces the column 0 with vector B. Okay, and that will give you the matrix A basket X required by the previous rule, right? That is same for A2. So X1 becomes, so X1 over here, don't be confused. Your X1, X2, okay, it could have been X1, X2. I was also saying X and Y, okay. Don't be confused. I just mean literally the same thing. Okay. So X1 over here is what? Your determinant of what? A1 over the determinant of A, and your determinant of A2. So over here, the A1 I was saying, the A superscript X I was saying initially is just A1. Okay, don't be confused. It's just the same thing, the same concept. X2 is the same thing. Okay. So over here we print experiments as X equal to X1, Y equal to X2. Just to explain what I was saying. I hope you understood me up to this point. Great. Now we are going to another concept. Okay. So as I said, um to be able to get your solutions, or to calculate for the unknowns, if you have ax equal to b, to calculate for some of your x, which is the unknown, okay, your x can have elements, some elements a, b, or in order not to be confused, we just say a c equal to b, okay, where c has elements x and y. So that unknown we are trying to find. Over here, the unknowns, were what? X1 and X2. Okay, don't be confused. The unknowns were X1 and X2. Okay, you always not see um X1, sorry, you always not see X and Y. You may see A, B, C, like you may see something, okay? You just have to understand what the elements of the unknowns are, what they are, so that you'll not mix things up. Okay, great. So we have this next concept, which is the matrix inverse. Okay, we said to find your unknowns, we can use the Kramer's rule, or we can also use the matrix inverse. Okay, great. So as usual, easy peasy, we have this expression over here, which is a NumPy expression to find your inverse of A. Okay, if you look at this equation, x equal to a power negative 1 times b, we have this, right? This. Okay. So this expression over here is trying to find your inverse of a. A, as usual, has already been defined in the previous cells. We've mentioned A over and over again. You don't need to type out A in this cell again because that's already been defined previously, right? So this tries to compute the inverse of A, as we all know. And it only works if the determinant of A is not equal to 0. True, right? You agree? Okay. And remember we confirmed earlier that the determinant was 3, right? So of course it's not equal to 0. If it was equal to 0, we can't even use this at the first place. We can't do all these things we are doing at the first place, right? So we found the inverse of A, okay. Then we have x underscore I envy. It's the same as this expression over here, x equal to A inverse times B. This, should I say, is it at symbol, this symbol over here? I don't know if you can see how I've highlighted it. Sorry. Uh-huh. This symbol, this symbol over here means matrix multiplication. Okay. So it's trying to do A inverse time matrix multiplication times your B, which is a vector. Okay. Very easy, right? And it gives you this, same as what the Cramer's rule gave us, 2.0 y equal to 4.0, right? Same thing here, it gave us the same thing here. Now the Gaussian elimination is also another way to solve for your unknowns. Okay, so these are several other concepts you can use to just find your unknowns, to find your x and y, to find some vector x in the equation ax equal to b, right? Great. So we have Gaussian elimination. If um, you didn't join last week's lectures, I'm hoping you can look at the recording because I did intensive um, explanation into Gaussian elimination. Okay, explaining it again will take a lot of our time. So this is just another concept. Of course, NumPy. Okay, sorry, please hold on. Okay, of course. Sorry. So this one is another library called SciPy. Sorry. So from SciPy dot this import this. Okay. So remember I said I've explained all over again what a Python library is, right? So this is also another library we can use for various computations called, so the library is called SciPy. So from SciPy dot this import this. These are the various methods we'll be using. Okay. So this, you see, this has, I mean, makes life easier for us. If you joined last week's lab, you realize that we were doing a lot, like we're doing a lot with just Python, trying to understand what Python really does. Okay, we're doing a lot with Python programming. But once we have Python libraries, it makes our life easier. It makes it easier to understand what exactly is happening, right? So we have this expression over here, which is trying to do Gaussian elimination internally. Then the next one is also trying to do backward substitution. Then what? It still gave us your answers as 2 and 4. All these, Cramer's rule, matrix inverse, Gaussian elimination. Gaussian elimination is a bit complex, especially if you don't really understand how it works, right? It's a bit complex. But there is also another way to solve for your unknowns, okay? This is also another way to solve for your unknowns. So now we are moving on to um what we call, okay, now we are moving on to this particular cell, which says the golden standard, sorry, the gold standard, how to solve AX equal to B in real machine learning code. Okay, so it tries to help us understand the various methods in which machine learning tries to find the unknown. Okay, so machine learning makes use of some Python libraries like scikit-learn, PyTorch, TensorFlow, and you know, I people actually use them, right? Great. So these are all the ways of solving a system. What is a system? A system is what? AX equal to B. X is that unknown we are looking for. Okay. X is that unknown we are looking for. So this is like a simple table, a simple overview. Okay, a simple overview to understand the various ways in which machine learning, okay, tries to find the unknowns. Okay, great. So we have this method, the solve method. And remember, we've used this, the np dot li blah blah blah, when we were solving the dot solve, when we were solving for using the Gaussian elimination. Sorry, yeah, Gaussian elimination. Okay, so we've used this before. This is also another standard way. We usually use it in regression tasks. Okay, we usually use this in regression tasks. Okay, so it's also used when you have more equations than the unknowns. Okay, more equations than the unknowns. LU decomposition, single value decomposition, and that's what says that we will explain tomorrow. Okay, and we have matrix inverse. But over here, what did you see? You realize that it gave you code example, the verdict. What did it say? It says almost never, and it says, I mean, I'm trying to avoid. Why? Because it's 2 to 10 times lower. It squares the condition number, hence amplifying rounding errors. Solving the inverse is like exterminating ants with a nuclear bomb. You understand what I mean. So what it's trying to say is all these things are acceptable. The gold standard is for regression is these two. The ones, I hope you can see where the pointer is pointing. These two. Then you do composition. We can use it. QR single value and decomposition we can use it. But for matrix inverse, you should always try to avoid it. Or machine learning always tries to avoid it. Machine learning doesn't even use it at all. Okay. And true. So you say that but we can also use this to find the unknown. So why does machine learning even avoid it at the first place? Okay. So in the next cells, you'll be able to understand what I'm trying to say or what I mean, right? So this slide tries to question this particular slide tries to answer the question: how do professionals solve AX equal to B in real code? Right? In real code in machine learning, we make use of all these, but some way somehow you should try and avoid matrix inversion, unless maybe forced, unless you are being told to do, but you should always try to avoid it. Okay, so this, in order for this not to look like we are just saying abstract things. The subsequent lines of code will explain what I'm trying to say. So now that we've learned Kramer's rule, inverses, LU, here's what here's what real world machine learning systems do. Okay, so at some point, okay, when you're programming, you get to some point and you do model.fit. Model.fit is some concept in machine learning. I don't know if maybe some of you have done some machine learning before, but if you haven't to, that's fine. Okay, but there's a concept where we call model.fit and the scikit-learn, or when you run a PyTorch linear. Um, so these algorithms run under the hood, okay, but some way somehow this method never involves computing the matrix inverse. So these algorithms use all these, but some way somehow they never use the matrix inverse. Even though we've discovered from the very beginning that we can use matrix inverse to find your unknowns. Okay, let's move on to the next. Okay, so as usual, this solves the system AX equal to B. Easy, 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 good to go, right? So np dot this dot solve equal and this, right? Then it gives you your unknown to be 2, 4. You remember you've solved for the unknowns with several other methods. Several other methods. Okay. So this is just some examples you could try with. So instead of the A, we could put P there, we could put Q there, just to find what your unknowns will be. Okay, so if you want to get the document, sorry, the Jupyter notebook, you'll be able to print it yourself and understand what exactly happens. Now we move on to the next concept. It says why we never use inverse in practice. Hilbert's matrix demo. So this is some, should I say, mathematician demonstration or some scientists. Okay, there's always a proof for everything. Okay, so they are just trying to prove, or they're just trying to let you know why you should never attempt using inverse, even though you remember in the previous cell we used the inverse to find our unknowns. They are also saying again that we should use all other options but try to avoid matrix inverse. Great. So we have all these codes, plenty, plenty, plenty. um, I don't really expect you to understand, though. I'll just explain the concept behind what this Hilbert matrix demo means. Okay, right. So of course, if we take this, of course, we take this. Okay, it takes your matrix A, your matrix sum B, and as for A. Okay, it tries to automatically, okay, compute the unknown. Okay, so remember, of course, our unknown has always been A. Sorry, AX equals to B. Our unknown has always been that X. Okay, so X becomes what? A minus rest of minus 1 B. So this is okay. This is some we are trying to find. Okay, no, let me say it again so that you don't confuse yourself. We are finding the unknown, and this expression over here is some expression NumPy, okay, gives to you to help you compute the unknowns conceptually. And then we have this. We have this. What does it do? This one does the like automatic matrix multiplication. So it takes what the inverse of h, this, and that's matrix multiplication by this. Okay. These all these have been defined over here. All these have been defined over here. Okay. And then we have, sorry. Okay, so in order to really understand what I'm saying, okay, so what does it mean? It means we have some system of linear equation as what? H x equal to b. Okay, h x equal to b, right? There's a same concept. Don't be confused. H over here, this H, so H matrix H is assumed, okay, that H is assumed to be very, very ill conditioned. Okay. If I say very, very ill conditioned, it means almost singular. You understand what a singular matrix is? Okay. So we assume, okay, that's the assumption. That's the assumption. The person who proved this, okay, that was their assumption. Their assumption was that H, if we have H x equal to B, their assumption that H is very, very ill conditioned and is almost singular. Okay. And they gave us a true solution. Okay. They gave a true solution. Of course, we initially we said x is an unknown, but in this particular equation, they gave a true solution to be what? One, 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 one. I mean, depending on your dimension of your matrices. Okay. So they gave x to be one, 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 raised to the power t. Okay. What does it mean? T is transpose, right? As usual, as I'm saying it, it may sound abstract. So in order to follow, sometimes just be writing what I'm saying down. Okay. So what does it do? What is all this trying to do? This. What is it trying to do? So of course I've given you what H is, I've given you what X. Okay. What's X? They said X is known to be the true solution. X is known to be the true solution. Okay. And over here it defined X as this MP dot ones, and N is the dimension, which is 10. What does it mean? Million one is one 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 10, right? B underscore H is what? H some matrix multiplication times X. You agree, right? Great. So what is all this thing trying to do? It tries to compare, like it compares a solution computed using matrix inverse. This, this over here, this thing, this, right? And it also tries to compute a solution using the np dot linalg dot solve, this method over here. Okay, that is LU. So it tries to use inverse, it tries to use LU. And what is all this trying to tell us? So this shows how badly the inverse performs when the matrix is ill conditioned. What is all these things I'm trying to say? Okay. So this is just like an abstract, okay, or how do I say, something like a theory, okay. So the Hilbert matrix is famous for being mathematically valid, but extremely ill or almost singular. Okay, great. So this expression is equal to Hilbert's to bracket n. Of course, you don't really need to know. We're just trying to prove why you should never use the inverse. Okay, you don't really need to know all this. We're just trying to prove why machine learning models in fact, they don't use it at all, and why you should also try to avoid it. Okay, So the age, that age is equal to 1 over ij minus 1. Like that is the whole expression for it. I mean, of course, don't bother yourself to understand it. Study even teach it. Okay, this is just some concept you should know, or like you should just familiarize yourself with. Okay, and then we have this. So this expression over here, of course, I don't really expect you to understand this line of code. I just want you to appreciate why the inverse is like never used. Okay, so this expression, the one I've highlighted, okay, the condition number tells you how unstable the matrix is. Okay, so for Hilbert matrix, the number is a bit large. It could be 10 raised to the power 13, you know. So what does it do? Look at this this particular expression. This particular expression. Okay, what is it trying to do? It's trying to calculate the length. You remember dot norm, right? The, okay, it's okay, length, magnitude. Okay, so it does, of course, this is very simple math. X underscore E is that E exact. That was the NP dot ones we defined earlier, minus your inverse that we calculated. So minus X, um sorry, I shouldn't say it like that. So it does X underscore exact, one we've defined, minus your unknown. Okay, I hope you are getting me. Don't be confused. Same thing for this. It tries to do we've already defined it here minus that. And what does it do? It's trying to find the magnitude, the length. In machine learning, we call that error. Okay, in machine learning, we call this error. Magnitude, then we call it error. Okay, it's trying to calculate the error or that length between both of them. Okay, from the inverse, if you compare the error when you use the explicit inverse, you realize that it is much huge, or it is huge as compared to when you do the LU decomposition. Okay, with this. Okay, so this is just an explicit way to prove to you why the matrix inverse, the explicit inverse, is never used. Okay, because the error it produces is much huge. So these are just concepts in machine learning, just to understand. Okay, that even if there's an error, because of matrix inverse, it becomes way huge. That's what we are trying to say. So try as much as possible to avoid the matrix inverse. Okay, because of the errors. The errors it gives you is way huge, way much bigger, okay, than the errors the other models could have given you, right? Okay, hope everything is clear up to this point. See how many minutes left. Okay, 31 minutes left. So we are going to some visualization. Of course, there's no need to understand this, just for you to understand the concept. So let me reduce the font so that it can fit. Okay, so we have this visualization, right? And plotting is also another way to find your unknown. So you remember we said to find your unknown, we have Kramer's rule, matrix inverse, and we understood why matrix inverse should always be avoided, why we shouldn't use it at the first place. We have Gaussian elimination, you know, all these um concepts to find you to help you find your unknowns, right? All these concepts to help you find your unknown. There's also another way to find your unknown, and that is by some visualization, doing some visualization. Okay, so this plot you see over here, it shows how solving it shows that solving a system of equations is the same as finding where their graphs intersect. Okay, so all this while we've been solving maths, finding our unknowns. Another way to also see it easily is to spot where exactly the two lines intersect. So 5 plus 2y equal to -2 is one line, which is the blue, and -4x plus y equal to -4 is also another line. And you realize that they intersect at some point. Okay, they intersect at some point, 2, 4. And you agree with me that the unknowns we've been finding from the very beginning, from Cramer's rule, all these were just 2, 4, 2, 4, 2, 4. And this graph proved exactly that the solution is what, 2, 4, or that unknown that unknown is 2, 4. I hope you understand me up to this point. Okay, so if there's an intersection point, what does it mean? Of course, the determinant is not equal to 0 and the matrix is really inevitable. Okay, now we're moving on to another concept. We're almost done. We're almost done. I think this is the last but one concept. Hopefully, I'll finish within the 28 minutes we have. We are moving on to another concept. Okay, linear regression. Linear regression is one of, you know, the machine learning models we have. Usually when you're learning machine learning, the very first thing you get introduced to is linear regression. Linear regression has been used to do a lot of things, make a lot of predictions, you know, but practically one skill set is which is good to have, right? Great. So linear regression works based on some normal equations we have here. Okay, so we have x raised to the power t or x transpose x t some theta equal to what? Y. One step at a time. Don't be confused. Okay, so we have this x and y defined over here. Of course, what are we trying to find? We are trying to find theta. We are trying to find theta. You understand the relevance of theta soon, but we are trying to find theta. Okay, and I mean, theta is this we have over here. Theta, of course, theta is your unknown. You agree, right? Theta is your unknown. And to find unknown, we've been able to understand that the best to use is the np.linalg.solve from that particular method from NumPy. So this thing I've highlighted over here is trying to do exactly this. Okay, so like in explicit terms, okay, in explicit terms, is theta is equal to the expression in brackets in front of theta, which is x t dot x raised to the power -1 times that whole expression x t dot y. Or let me say conceptually, this is how you find theta. But the correct method to use is this. Okay, so that is the complete computation is trying to do over here. So we are trying to find theta. We have our x defined as this, we have our y defined as this. You understand very soon why the x is this way. Okay, why the x has to be this way, why the x is this way. Okay, so then when you do that, when you print, or you're trying to print x, of course is this. When you print y, of course is that. Okay, and the best fit, or that okay, so let me give you the equation. So y is equal to theta, some theta naught plus some theta 1. Okay, so usually the unknowns you are trying to find. So if you say you have a is equal to b, and let's say this time your x has elements theta naught and theta 1. You understand me, right? Let's say now your x has element theta naught and theta 1. We are trying to find your unknown. You are trying to find theta naught, theta 1, right? So that is what this equation over here is trying to do. Remember, if we have two vectors, theta naught, theta 1, position in pattern matters the most, right? So then we pick the name, that is theta, square brackets, position 0. What is our position 0? Obviously, the element at position 0 is theta naught, and the element at position 1 is theta 1. Okay, so we are trying to find the unknowns, and the unknowns over here obviously has elements to be theta naught and theta 1. And that is what happened here. I hope you are following. So we over here we said the best fit is equal to y 1.0833 plus. Okay, that is it for this. Now we have this. We have this. Please follow. Follow so that you don't get confused. We have this. First of all, remember what I said, that for the x, okay, x. If we have x, we try to introduce a column of all ones, which is the intercept term. So over here you realize we have, if we are writing it in a column, okay, in a column, okay, you realize that your x then is equal to has column of 0, 1, column vectors of 0, 1, 2, 3, and 4. Column, okay, column, great. And now you remember during lectures, Seth taught us that we don't just write the x. We put we first put column of all ones, which represent the intercept term, because we have to make sure, or we have to make sure it does not find a way to pass through the origin in the plane. Okay, we have to make sure it does not find a way to pass through the origin. So we introduce an intercept term to be 10, to be 1, 1, 1. Okay, so you realize over here we just did x underscore data, just this. And that is where this comes in. That is where this comes in. This particular line of code that I've highlighted, that is where it comes in. What is it doing? You see, np.column stack, what is it doing? It is trying to stack a whole column of just ones. One, 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 one. Okay, it's trying to stack a whole column of ones to this, x underscore data. What does it mean? It means we just get a whole matrix of what? Our matrix becomes 1 0 1 1 1 2 1 3 and 1 4. Okay, that becomes our new matrix. And that is how we want it. You realize that when we're solving, when we're doing this, we were already sorted. We didn't need to do anything. We didn't need to do column stacking. Okay, we didn't need to add one column to another. Okay, so we realize that this x is already in a way we want it. X is already in the way we want it. That is, it has first columns of just ones, which is the intercept term. It has this, right? Great. But this didn't have it. This gave you just x underscore data, and it gives you this column. But we don't want it that way, right? We don't want it that way. We don't want the line to by force pass through the origin. So then we introduce, and mind you, this only affects the x. The y is never touched. The y, we like the y the way it is, but it only affects the x. Okay. So then we introduce a column, a whole column full of ones. Okay. Then we stack that column to this. Okay. And now we get a whole matrix of 1, 0, 1, 1, 1, 2, 1, 3, and 1, 4. And of course, with all that, we come and do a simple computation here to find the unknowns, which is theta 1 and theta 2. We round it to 3 and we get theta 1 and theta 2 to be 3, 2. Okay, or you can write the equation as y equal to 3 plus 2x. Great. I hope I am hoping you understand me up to this point. So the column ones in the design matrix allows the model to learn a y-intercept, which is a bias term. Okay, and without it, the model is forced to pass through the origin, which is rarely correct well in raw data and leads to systematically biased predictions. Okay, the predictions then becomes biased, but we want the model to learn. We want the model to learn. Okay, great. So this is just a simple visualization to understand why we truly need columns of ones. Okay, why we truly need columns of ones. So that is the data point without intercepts. It passes through the origin with no intercepts. Sorry, sorry. Let me repeat it again. Let me repeat it again. So this is the data points, right? So with intercepts, it gives you this. Then with no intercept, it gives you this. Okay, it's passing through the origin. Okay, don't be confused. Look at where the zero is. Look at where the zero is. So we have negative 1, 0, 1, 2, 3, right? So when there's no intercept, it's passing through the origin, which is 0, 0. But when there's truly intercept, which we introduce as 1, 1, 1, 1, then it truly passes through the data point. Okay. We have like 80 minutes left. Hopefully we'll finish soon. Then we have linear regression and we have polynomial regression. So instead of a straight line, we usually see a curve. Okay, instead of a straight line passing through the data point, we usually see a curve. Great. Okay. Now, please hold on. So this is you know, another line of codes trying to do some polynomial regression. Okay. So for a quadratic model, a linear model is y equal to theta naught plus theta 1 x. But for a quadratic model, okay, we have y is equal to theta naught plus theta 1 x plus theta 2 x power 2, or x raised to the power 2. Let me say it again. So for the linear regression or the linear model we did above, we're just looking for two truly we're looking for the unknown, but the unknowns had just two elements, which was theta naught and theta 1. But for the quadratic model, we are looking for three different elements in which are the I mean we are looking for the unknown, all right, but the unknown has three different elements, which is theta naught, theta 1, and theta 2. And then I'm describing the model, or I'm saying the model is y is equal to theta naught plus theta 1x plus, okay, that alone will give you linear. But to make it quadratic, it becomes theta naught plus theta 1x plus theta 2 times x raised to the power 2. Theta 2 times x raised to the power 2. That is exactly what I'm saying, right? So over here, we realize that the true parameters, or of course, is this is trying to do This is just trying to follow this formula. What we've been doing from the very beginning, this. Okay, just trying to follow it. NumPy, since we are making use of NumPy, trying to make our life easier by finding the unknowns with it. So the dot solve, okay, it's just doing exactly that. When we round it to 4, it gives us our unknowns to be 3, 2, and 0. Okay, over here we realize what do we realize? Realize theta naught is what? 3, 2, theta 1 is 2, and theta 2 is 0. Now, someone will ask, theta 2 is 0, right? So okay, wait, before I explain the meaning of theta 2 being equal to 0, okay, I want to let us picture how this would look like this. The one I've highlighted. What is it doing? It's doing a column stack. It is stacking it's a stacking elements of one, so values of one. So if you have a matrix, the first column will be 1 1 1 1. And the second column is x data. What was our x data? X data was defined earlier as this. Where is it? Our x data was defined earlier as this. This. Okay. So then our second column becomes 0 1 2 3 4. Okay. Then it is also stacking x raised to the power 2. Makes sense, right? You remember the quadratic model equation. It is y is equal to theta naught plus theta 1 x plus theta 2 x raised to the power 2. Okay, so then the next column of equations will be x data. So all the values of x data, all the elements of x data, power them to 2, raise them to 2, or so it will be 0 times 0, 1 times 1, like that. Okay, so then we have 0 1 4 9 and what 16. Okay, so that becomes a whole matrix. So your matrix becomes 1 0 0 1 1 1 1 2 4 1 3 9 1 4 16. Okay, great. And of course it tries to do all these by finding the unknowns. Easy, right? Making our lives easier, and it gives you this. Okay, so next I was trying to explain what we mean by um why we got theta 2 to be 0. Okay, we are trying to find our number. Why should theta 2 be 0? What does it mean? Okay, it means that the x per 2 term wasn't necessary. Why? Because when we calculated um when we calculated initially, we got the intercept. Okay, when we use the linear model, we got the intercept, which is theta naught to be 3 and theta 1 to be 2, which was the slope. What does it mean? It means the line was perfectly linear and not curved. Okay, so there's no curvature. The theta 2 means the theta 2 equal to 0 means there's no curvature. The um the line is completely the model is completely linear. The line is completely linear. There is no curvature. If theta 2 was equal to 3 or some value, then we can say that it has some curvature. Okay. So this is a visualization to explain what I'm saying. So if I say curvature, a curve like this, okay, that's what I mean. So sometimes, so for the polynomial regression, we give, we say one is the intercept, x, and the linear term x power 2, x raised to the power 2 refers to the curvature term. Okay, so depending on its value, you'll know how much it curves. Okay, great. And once it's 0, it means there's no curvature. The line should be completely linear to fit your data. Great. So so this is some polynomial regression. This is its data I defined over here. This. Okay, it defined some random data over here. Okay. So the start is -2, end is 5, step of 2, right? Great. Then, so those are the points, okay? Those are the points. So it says, if you look at it, it says dots, the black dots represent some noisy data. What does it mean? Like the points are just scattered all around. Then we have the linear fit or a linear model, okay? And then we have a quadratic fit. And realize that the quadratic fit was perfect. It, like, even though it didn't fit all the points completely, at least it was much better than you even going for a linear. Okay, what does it mean? Sometimes depending on how the data is, solving with linear regression is enough. Sometimes you have to go ahead and make use of polynomial regression so that it can properly fit the point you have. Okay, great. So you see this point, you see this visualization, you realize that the linear model wasn't needed here, the quadratic model was needed here, and it had what does it mean? It means that the term for theta 2 is not zero, right? It has some value which represents its curvature or how much the line will curve. So that is it for today. So this is just like, should I say, killer wait here, right? So these are some visualization codes, and these are some visualization codes. Let me see if I can squeeze it for everything to fit. So this is just a breakdown of what we've been doing since, you know, a breakdown of what we've been doing since. So we have this visualization showing four different plots, right? Showing four different plots. So the first panel is the determinant, which is the signed area scaling factor. So realize that, which is on the top left, realize that the blue square is a unit square. We define it as a unit square, as we can see it for ourselves, right? Then the orange shape, it kind of looking kind of slanted, parallelogram kind of somehow, you know, happens after you square the units, after you square the uh, after you square the unit square by the matrix A, you realize that the area becomes three times bigger. Okay, that is what I'm trying to say. I've already explained. So what does it teach us? It teaches us that the determinant tells you how much a linear transformation can stretch or flip the area. Okay, that is what the determinant, that is how important the determinant is. And then we have panel B, which is the top right. Okay, solving for, some linear systems, which is AS equal to B. Okay, of course, we've already explained this. We said that these are two different lines. This is also another way to find your unknown. And to find your unknown, the red dot represents our solutions or represents the unknown. That is the point at which the two lines intersect. Okay. So this shows that solving a system of linear equations is geometrically finding where both equations are true at the same time. Okay. So this is just some concept. And then we have the bottom left, which is um, intercept, which is equal to columns of ones in a design matrix. We have your data points with intercept. We have this, and when we try to force the model to pass through the origin, we get this. So what does it mean? So the black dots, of course, are the various data points. Then the green line is the line with an intercept. You remember in the matrix when we introduced the 111 column, that is the intercept term. And the red dash line is the regression line that is forced through the origin. It has no intercept. And ideally, we can see it technically that it is wrong. It is not even fitting any of the data points, okay? It's not fitting any of the data points, okay? And that is the problem. So what does it mean? What does all this mean? This demonstrates that we include a column of ones in the design matrix so that the model can learn the intercept. Okay, so that the model can learn the intercept. And then we have panel 4, which is the polynomial regression. Okay, the polynomial regression, which is equal to extra columns in X. What does it mean? What is that extra column? It is the X power 2 term, right? And over here, we realize that depending on the nature of the data set, when you use a linear model, it's not the best, like it's not the best option. Okay. Sometimes going for a polynomial regression is the best option for you, right? Great. So then the design matrix will have features like 1x and x power 2. The linear model will have 1 and x. You agree, right? Great. So what's what are we trying to say, or what am I trying to say? This teaches that when you add the powers of x, okay, it gives the model more flexibility to fit nonlinear shapes. Okay, so depending on how the data is being scattered, sometimes it is good to increase or to add an extra term, or add, yeah, an extra term of, or adding powers of x, okay, to give or to make the model a bit flexible instead of being so rigid and linear. You make it a bit flexible to fit your non-linear shapes. Okay, so the overall purpose of the figure is to understand that determinants describe how matrices can distort shape, okay, how one particular matrix can be transformed to another because of some matrix, okay, and how linear systems can solve by finding the intersection of the geometric constraints, and how linear regression needs an intercept that is a whole column of ones, right, to avoid bias fit or to avoid giving you biased predictions, and how the linear regression is just sorry, how the polynomial regression is just a linear regression but has extra columns for a higher order terms, so to make the model a bit flexible to fit your data points. Okay, and this is just the end of it. So wow, I finished on time today. So in summary, in um in machine learning applications, okay, we make use of either LU or Gaussian. You can make use of either LU or Gaussian, and the one that is recommended the most is this. That is the LU decomposition. Okay, this is also another concept that sometimes is used in regression, but never use matrix inverse, or machine learning models do not use this term, okay, they do not do matrix inverse at all because of the error it gives you. Of course, you remember Sir said that no model is perfect. Some way somehow you get an error, but you have to make sure your error is not so huge to affect your predictions, okay. And you realize that when we did the matrix inverse, we were getting an error, okay, bigger or huge than the other options we used, okay. And that is why we do not use it at all, because why should, I mean, the errors be much bigger than other models, okay? Why should we even use it at the first place? Why not explore other options to give you a prediction that is closer to the main target? So this is some mini exercise, and I can make the recording available to you. But until then, do you have any questions? If not, thank you for having me and see you next week.